For my Sped talk, I would like to focus on some of the usefulness of discrete simulation. First off, with most people are familiar with within simulation is real-time simulation. You can see this often in a video game, for example. Everything is happening in real time. There's often a physics engine involved. When you move, you take steps that take a certain amount of time. It's very useful for some applications such as video games or other things like that, and can be sped up for, say, other different types of simulations, but it's also very resource intensive because you need a lot of background. Again, going back to the video games, you need the physics engine, you need to know how to walk, how everything interacts. And this is where discrete simulation can become a very powerful tool for simulating real world problems such as warehouses, movie theaters, and stores. Discrete simulation is not real time. So if you have, say, a warehouse that has a bunch of operating forklifts and they're moving pallets everywhere, their normal operations during the day, the event or the simulation is going, and then say all the shifts close and no one's working at all. A discrete event simulation only focuses on the events. So if nothing is happening in the warehouse, it'll skip to the next event. So you don't have to waste all of that time within a real-time simulation, and try to speed that up. Discrete event simulation also focuses on the very key aspects of a system. So say, take that warehouse example again, it doesn't need to focus really on the physics engine of all the forklifts and how the pallets move and what's inhibiting them. It just needs to know the wait times that it takes for a forklift to drop off a pallet. So it's very lightweight and fast compared to a lot of other systems. Discrete event simulation is also very useful for finding bottlenecks within real time. It's often hard to see where everything's backing up. So for my little test here that I have, it's in Python, and it's using a library called SymPy, a very simple discrete event simulation library. And in this, I've built just a very simple grocery store where you have a bunch of random shoppers coming in. They come in every 5 or so minutes. They have some random items from 5 to 10 items. And within the store, you have a number of cashiers, a number of aisles where you can get your food, and a number of exit doors. And each of these have different process delays. So say like a cashier takes 5 or so minutes to take your groceries and go to the cashier and get through the line. Or it takes a couple minutes to go through an aisle, or it takes a couple of seconds to go through a door. So if we run this now with just one cashier, one aisle, and one door, we can see that we have, 20 or so shoppers that leave the store successfully. And if we, say, increase the number of doors to 10 and run it again, we see about the same. So our bottleneck is not the doors. So if we put that back down to 1 and we try cashiers, up that to 10, we see the same, that we have about 20 or so shoppers. So we know that our cashiers or our doors is not the bottleneck. But if we increase the number of aisles in our store simulation, we see that a bunch more shoppers go through. We found our one bottleneck in this very simple simulation. And you can get as complicated or accurate in your discrete simulation as you want, and you can really simulate different warehouses, banks, any really real world building where people are coming and going, and they're spending certain number of times doing certain number of actions, where you don't need a real-time simulation. You can get this done so fast and find all the bottlenecks and different resources that are being utilized. So we know that our aisles might be a problem, and we might need to boost those up, or we might need less cashiers than we thought we did. It's very helpful in real world situations to use discrete simulation.